Welcome to Equinox, where Rob and I are striking the balance between the light and the dark. This is episode 20. My name is Joseph Darnell, and I'm joined by my good friend, Dr. Robert Carter. Hello, Rob.
Hello, Joe.
It is so nice to be back on the airwaves again. Love this little space that we have in people's ears. Hey, everyone. How you doing? Rob, how you doing?
I'm doing great.
What have you been up to lately? You done any new videos? Got anything new on biblical genetics?
Yeah, actually, my new episode, I call it Privacy is Dead.
Interesting. Yeah, that's good.
I started off with there is no privacy online, which everyone should know, though most people don't realize that nothing is secret online. And then I went to there is nothing secret in genetics anymore. No adoptions are secret, no cases of infidelity that resulted in a child, no unwed marriages, no kidnappings, and murder and rape are no longer private things because we can now pull DNA out of very old laboratory crime scene samples and identify people positively. But then I spun it into there's no privacy before the God of this universe. And nothing we do is hidden. And in the end, everything will be revealed.
So true.
And I made it into a gospel message.
What has been the response to your video?
Well, that one hasn't gone up yet. It's going up tomorrow night.
Oh, excellent. By the time this episode comes out, that episode will already be out.
Yeah,
we'll have to throw that into the show notes. So if anybody wants to get a hold of that, you'll see the response from the link in the show notes. Speaking of YouTube, there is something else going on.
Yeah, something exciting. Great job, Joe.
Thank you. As we talked about last time on episode 19, we wanted to get Equinox available on YouTube and debated whether or not we would include all of the back episodes 1 through 19. And I hesitated just because YouTube doesn't have a way for me to input that was really, episode 1 was released back in February and actually backdate the episode on YouTube so that it appears to be back in time. You can do this on blogs, and I really love that feature when you're updating a website and you want to move your website platform to a new platform. You can keep the historical information. And so I just hesitated because I didn't want to bombard YouTube and say, here's 20 new episodes available today, guys. Like, everything is new. I didn't want people to think that I was spamming the channel and just garnering for new attention or something. So the good news is all the episodes are there because any completionist who wants to just hit play can use the playlist and listen to all of the entire series if that is what they want to do. And if they want to just catch the latest, it'll be available if you subscribe to the channel. How do you feel about listening to podcasts and other audio content on YouTube yourself?
I know a lot of people that do it. I don't myself.
I do it some of the time.
I guess if there were things available, I might do it more if I was aware of it. But all my podcasting, I do when I'm driving or waiting online or something like that.
It makes a lot of sense, yeah. I have the same limitation.
During the day, because I have to read for a living, I listen to music, but I don't listen to people talking.
Yeah.
It's not possible.
I have a real hard time listening to any music with lyrics while I'm editing video content. And I can't do it while I'm editing audio content. But I love to listen to podcasts while I'm doing some graphic design in Photoshop. So I actually use a desktop application for that sort of thing.
That makes sense, but I don't ever do stuff like that. Well, good. So we have now more options for our audience to experience Equinox. That's really cool.
Yeah, and it might be easier if anyone wanted to comment on an episode. If that is sort of your thing already, you don't like listening to podcasts in Spotify and Apple's podcasts because you don't necessarily get the ability to comment. I know one of the reasons that people do enjoy the content in YouTube is that if they do pay for one of the YouTube premium features, they are able to listen to shows outside of the player or while their phones are asleep.
Cool.
So an advantage of, already having a subscription to that YouTube feature is that if they did want to subscribe to podcasts, they could listen to them passively through YouTube. And then they can still join in the comments.
Oh, that's really cool. I didn't know any of that.
I don't do that, but I could definitely see the advantage of moving over to that platform for that kind of reason. So we'll just see where it goes. There will be a link to the YouTube channel available in the show notes from this moment forward, but I recommend the best experience if you want to get to the show notes or just have a great audio player that you continue to listen to the show in a regular podcast app on your favorite device.
Very well. And it's easy to find.
Now, you're still listening to the podcast too, right? Do you have any new YouTube channels that you're checking out? Anything new?
No, not really. Not since last time we talked. I don't spend a lot of time on YouTube, honestly. Who's got time for that?
Do you spend most of your time on the social media networking platforms?
Not really.
If you've got time to spare?
Yeah. I'll troll, Facebook a little bit. I'll get on Twitter and see that no one's tweeted at me, and I'll try to do something on Parler, which is frustrating because I don't have 1 million followers like some other people.
Oh, I see. So, and to get anywhere in social media these days, you at least need 100,000 followers to start with.
It is unbelievable.
Other than that, is Parler everything that you hoped and dreamed it could be? You brought it up a couple of episodes ago, and you got me curious. Is it going to flesh out?
It's like a giant nothing burger, actually. That's been my experience so far. It's like you get on there like, oh, I'm going to get all these new friends. And no, it's the same people I interact with on Facebook who happen to be on Parler have found me. A few people I don't know, but not that many.
Yeah.
It doesn't explode as I started posting things. And so there's just this social media thing that I, as a total introverted nerd, am not good at. And that is networking and interacting with people. I'd rather sit in the corner and cackle over some new discovery than go out there and try to actually win friends. So,
it is so hard. It's not human. It's not natural. I've heard some research studies that explained that the way that we feel after interacting with people in social media does give us the dopamine that we enjoy. And that is the part of the equation that can also be addictive. But on the flip side, one thing that social media experiences don't usually satisfy is any sense of loneliness or the lack of a real human interaction.
Yeah.
That having real human interaction can do.
Yeah.
Yeah, it's not a win entirely with social media. I'm not a big fan. I actually feel more connected to people I listen to on podcasts than most social media.
Oh man, someone like Brian at the Daily Audio Bible.
Yeah, he is good, and his daughter.
Every time I listen to that most mornings, and I say good morning to him. Even though I'm just listening because he says good morning. I say good morning.
It's so natural.
It is because he's like my friend.
I totally get it. And when I'm like I have subscriptions, I've been listening to some of these guys for 10 years. I cannot get a hold of people that I've been connected to on Facebook for 10 years. I mean, like I cannot reach them.
I've been listening to Daily Audio Bible for about 10 years.
That's an excellent app. By the way, anyone who wants a good daily audio Bible experience, that's the one you want to get. It's check it out for sure.
Yeah. Excellent stuff. Hey, we have an announcement to make that you didn't realize.
What is that?
This is a milestone. This is show number 20.
It is a pretty big deal.
Woo! I mean, it's not like 50 or 100 or, but 20 is a nice round number. And I'm very happy that we've been doing this now for 5 months. I'm loving this podcast.
I figured it was good enough that we should be on YouTube now. We should do something special for the occasion. So yeah, I'm glad that we reached 20. You never really know with a podcast how far it's going to go.
Yeah.
I'm really happy with our discussions. I think that we have so much in common and interests. You have so much to share. It is awesome. I'm curious to see where we go with it in the future.
We make a good team also because you ask excellent questions and you really guide a conversation that I might not be able to have.
Yeah.
Or not for someone like you saying, well, wait a minute, what does that mean? Oh, I never thought of explaining that before. So
yeah,
we got a good routine going here, and I'm really, really, really enjoying this.
Yeah, practice makes perfect. A lot of people wouldn't know this. I've been on a few hundred other podcasts, episodes of other shows, but this is your first. Like you've been on interviews over your career.
Oh, tons, yeah.
But you haven't had a podcast before, right?
No, never ever.
Speaking of which, I'm really interested in this here main topic. You want to get to it?
Well, yes, I'm dying to. I'm actually rocking back and forth with excitement about how fun this is going to be. But, you said you never know how far a podcast is going to go. I can guarantee that we're not going to get to the end of my notes here. And even then, when we do get to the end of the notes, there's going to be 5 or 6 or 7 or 20 more podcasts on similar themes to get at the heart of what is being discussed.
Excellent.
Because as I started researching this, I had to keep going back in time and go over here and go over there. Because I'm trying to think of, if I wanted to explain this to somebody, how would I do it? And the question is, what is inside an atom?
All right. Sound the chime. Okay, so what is inside of an atom? I actually saw like a photograph of atoms of, I think, a gold bar. It just looked like a gold bar up close. Like I was really disappointed.
Well, the images that we do have from atoms, from scanning tunneling microscopes, where they take a crystalline point with a charge on it and they scan it back and forth over a surface. And if you do that very finely detailed, you can actually image an atom, and it looks like a fuzzy blob.
Yeah. Huh. So does that fuzzy blob look different from different kinds of minerals and objects?
Different sizes, yeah.
Yeah.
So if you can take a very, very cold plate and you can get an atom to just cool off and stick to it, then you can scan it back and forth, usually a big atom, and you can scan it and you see this fuzzy blob. And you can see different sizes of atoms, and you can see some molecules, but that's it. And even then, it's not a picture.
Wait, so this is new to me. I don't understand how I missed this. Different atoms come in different sizes?
Oh, yes. Yes, hydrogen is the smallest atom.
How big can the biggest atom be compared to the smallest atom?
That's an excellent question. I don't...
Like, are we talking about the difference between like a tennis ball is to a beach ball?
I bet it's more than that.
I didn't realize that. I just thought that an atom, because an atom is made up of essential ingredients, I just thought of it as one size fits all atoms.
I just Googled it. Atomic radius on Wikipedia says between 30 and 300 picometers. So it's a range of about 10.
Okay.
Another site says a range of about 5. So take a tennis ball and make it 5 times larger. I don't know, a little smaller than a soccer ball.
Yeah.
Because if you get bigger than that, they get unstable and they start to break apart. And that's why all of the elements at the end of the periodic table are radioactive, because they're simply not stable. Too many moving parts.
In a nutshell, can you explain then what is happening to an atom when it's going radioactive? Is it just coming apart?
Exactly. It's coming apart. The nucleus, there's pieces of it breaking off. The forces inside the nucleus aren't able to hold all the parts together, and parts go whee, and they fly away.
Yeah. Huh.
So, okay, ready?
Yeah, back up to the beginning about atoms.
How do you start this is the question, and I still don't actually know. You want to go back to the Greeks?
Oh, sure.
Or you want to go to Benjamin Franklin? Let's start with Benjamin Franklin.
Okay.
He made
He's not very Greek.
No. But he is pre-atomic theory scientist, and he made a giant mistake that has plagued us ever since.
Oh, okay.
For instance, open up the hood of your car and look at the battery. There's 2 terminals in the battery. One is black and one is red.
Yeah.
One of those terminals is attached to the frame of the car. Which one?
Oh.
The black one.
The black one? Okay.
And that's the negative terminal.
Okay, because it's black. Black is negative.
But when we talk about current flow, we talk about the current flowing out of the battery, flowing to the starter through a wire. And then the starter doesn't have a wire that goes back to the battery again. They just screw it to the frame of the car. And the current returns through the frame of the car to the black terminal. That's the way the current flows.
Okay.
But the electrons go the opposite direction. Electrons have a negative charge. They flow from the black terminal through the frame of the car, through the starter, and back to the positive terminal.
Oh, dear. Then why haven't we learned from this mistake?
Because back in the day, Ben Franklin knew there was this thing called static electricity. So he could rub a piece of amber. Today we use balloons, right? You rub a balloon and you know it'll stick to your hair. And he figured out that something is being transferred from this side to this side, but he didn't know which way it was being transferred. And he knew that if you took one of these things and you took a bell jar with a little electrode on top and there's a piece of gold foil hanging in it with 2 leaves. And if you touch a charged thing to that thing, the leaves of the foil will pop apart. So he says there's something in there. These things are repelling each other. like charges repel. That's what they figured out. And he says, I'm going to guess that this side is positive and this side is negative, and there's a substance going from this side to that side. But he was wrong. He got it backwards. This is why electrons have negative charge. And so if you look at any electrical diagram, you'll see these little symbols. They look like crow's feet. That's a ground symbol. That's just ground. So you take all your wires from your battery or your power source and you run them through your computer chips and your diodes and your transistors, and when you're all done with them, you just draw a little ground symbol. It just goes back to ground. And electrical engineers forever have talked about current flowing through a circuit, but actually the electrons are going the opposite direction.
Wow.
They come from ground, go through all your circuits, and go because they want to think positive. They don't want a negative sign in all their calculations. You know what it's like in math?
Yeah.
How many times in high school did you forget the negative sign and you got marked off for it?
Bro, yeah.
And they don't want every single calculation to have a negative sign, so they just ignore it and they go backwards.
Wow.
Because of Ben Franklin.
Oh, that is huge. That is a huge mistake to be mainstream. Wow.
So that was over 100 years before we knew what an atom was. But this is just the beginnings of it.
How does the energy have to do with the atom then?
Oh, boy.
Speaking of which, if you want to learn more about energy, you've got to go back to episode 19,
Yes. At the end of this discussion, hopefully, we're going to get to electrons and the two types of quarks that are the fundamental particles of the universe. These three things do not break down. They are just little packets of energy, and everything else is built upon them. Protons and neutrons and everything else. But we can't get there yet. That's the end of the discussion. First, we got to figure out what an atom is. You ready?
Yes, please. Lay it on.
All right. So we knew for a long time that there are some things that can transform into other things and some things that can't. And we figured out that there are these things called elements. And Dmitry Mendeleev, the Russian chemist, figured out that there's a periodicity to these elements. And he invented what we call the periodic table. And once he did that, people said, wait a minute, there's a hole in the table. And they went out and found the element that was missing and plugged it into that place. Really cool. And so our discovery of elements accelerated greatly in the end of the 1800s because now we had a way of thinking about them. And we went out and we found all the missing ones.
Okay.
So all those weird things that go into your cell phone, that those poor kids in Africa are digging in the mud hole to get this rare element out so that Apple can make your iPhone for you in a slave market in China. Those strange elements.
Yeah.
Those are the things that were discovered during this period because iron and copper, those things are already known. All right. So now we have this concept that there are things that are different from each other and you can't transform them to other things. They are an element.
Right.
And we knew that elements were made of particles. We call them atoms. And that they're tiny. We knew they were tiny. But we didn't know what the atom was made of. So one of the classic ideas of what an atom was, we call it the plum pudding model. Now, plum pudding doesn't make any sense to an American. How about rice pudding? You ever have rice pudding?
Yeah. I mean, it's nothing special, but
it's got raisins in it, right?
Yeah, that's
rice and raisins. Okay. So for someone of English extraction, they would talk about plum pudding, which is pudding with little black chunks of plum in it.
Mm-hmm. Yeah, not my thing.
And so the idea was this. What if an atom is like a plum pudding? That is, the positive charge, because we knew electrons existed because of Ben Franklin and others, but the positive charge, we didn't know what it was. What if the positive charge was this substance, and embedded into it were electrons, like plums in a pudding? Sort of like a taffy.
Yeah.
And inside that taffy was little crunchy bits of sugar, colored sugar, something like that. I'm trying to think of another example. Can't really think of one.
No, I'm really interested in the desserts and candy category, the sweets. This is good.
Oh, yeah, I like this too. This is good. So from here on out, though, as we start figuring out what's inside an atom, the reason I'm struggling to explain this is because I don't like people to take things on faith. I like to explain why something is true. But in order to get this discussion going, you have to take a few things on faith at first, and then they get explained as we go through. And this is very confusing to a lot of people. So people's eyes glaze over.
So that in order to really learn and understand and create useful knowledge, we have to base it on a few things that we cannot prove.
Yes. Especially when we start talking about the inside of a proton or the inside of a neutron, because we know they're made of particles.
Would it be fair to say that we could be all wrong about this stuff, or is our theory so well presented and circumstantial evidence backs it up so well that, like you're saying, we cannot verify it with scientific confirmation, but we're just really close?
Have you heard of the Higgs boson, the so-called God particle that they discovered at CERN, the big collider in Switzerland?
Yeah.
They spent a couple of $1 billion trying to track down the last of the fundamental parts of matter. And in so doing, they found out it was exactly like what they had expected. So they spent, a couple $1 billion tracking down a prediction, and it was exactly what they predicted. There is no reason to question the standard model of the atom. The parts are the parts. In fact, a lot of physicists were very disappointed that what they found was what they expected, because that means there's nothing exotic, there's nothing new. And they're sitting there scratching their heads like, well, we wanted to learn something new. We wanted to break something and discover, oh, it's not the way we thought it was after all. But no, it's exactly the way we thought it was. So in the end, things like particle accelerators and PET scans and MRI machines and all these things that are very important to our modern life is based on some assumptions we got to plow through before we see how it all works. And since it all works beautifully, the assumptions are probably correct, even if we can't prove that a quark exists because we've never seen one by itself. We know they exist because in different combinations we can see how they combine to do other things. So, literally, we are at the edge of what humans can do.
Yeah.
And it's amazing and fun and cool.
Wow. We just have to realign all of our textbooks to represent the positive and negative energy correctly, and then we'll really be making some headway.
No, too late. It'll never happen. Electrons are negative.
Wow.
Oh, well. All right. So, plum pudding model.
Yes.
Is that true, or is it something different? And how would you know? And I want to introduce a man named Ernst Rutherford. Now, Ernst is not a common name today, but the two Ernsts that we're going to talk about in the 20th century are two of the most important men in world history. They're both named Ernst.
Ooh.
The first one was Ernst Rutherford. He was the director of the Cavendish Laboratory in England. Now, we talked about Cavendish in our gravity episode.
Yes.
The Cavendish experiment was when he took those metal balls with a telescopic microscope, and he could look at the finest little movements, and he brought these balls together and figured out what the torsion was on a spring, and therefore he calculated the force of gravity between those two objects. So Cavendish, super important scientist, he founded the Cavendish Laboratory that 85 years or so later, Ernst Rutherford is running. And Rutherford was possibly the greatest experimental physicist in world history. He discovered the half-life of radioactive elements.
Ooh.
And figured out that it was a half-life. Oh, it's a cool concept. Hey, 10 years from now, there'll be half of that left. Oh, it's a half-life. 20 years from now, there'll only be a quarter. So that's his idea.
Right.
He discovered the element radon.
The element.
Extremely important element. Or radon, that here in Georgia, people have radiation detectors in their basements because we have a lot of granite in the basement rocks. And if your basement is improperly ventilated, it can build up radioactive radon to toxic levels, to levels that are harmful to human health. Well, that's Ernst Rutherford discovered radon. He discovered alpha particles. One of the three forms of radioactive decay is when radon releases a big fat helium atom, which later on we're going to learn has 2 protons and 2 neutrons. But he figured out that there's a form of decay called alpha decay, and it was helium.
Oh.
That's really cool. We're talking about 1900-ish. How do you figure that out anyway? And here we're talking about 1900s.
No.
Early 1900s. This guy's figuring this stuff out. He figured out beta decay.
Oh, that is awesome.
And he figured out that beta decay, what's coming out of the atom is a high energy electron. And what's cool is I've actually done this. You can make a cloud chamber. You can take alcohol and put it on dry ice, and it will make an alcohol cloud. And if you take a radon source, like maybe from your smoke detector, shall we say, and you hold it up to that cloud, you can see choo 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 choo. The little choo choo choos are big fat alpha particles moving slowly, and you can see them move. You can actually clock with your eyeball how fast these heliums are coming out of the radon atoms. And then the choom is every once in a while a beta decay, a really fast electron. And it's so fast, it's just there. And you see a streak, a straight streak, choom, and then it's gone. But the alpha particles are so big and heavy, yeah, they kind of travel in a straight line and they curve a little bit because they're just fat and slow. But the electrons go in a straight line. And you can see that. It's a really cool experiment. If you've never seen it yourself, YouTube is there. I'm certain that you can see this on YouTube. Really, really cool. He figured these things out. His laboratory, under his direction, they did the first controlled splitting of an atom. 1911.
That is incredible.
1945 is when we exploded the atom bomb. So that first splitting of the atom occurred before World War I, just before World War I. And at the end of World War II, we were blowing up cities with splitting atoms. This is how fast our knowledge is increasing. Literally, they went from, in the 1800s, the life of a person in the 1800s was not much different from the life of a person in Jesus' time.
Right.
As far as the technology goes. Now, we had better houses and, we had better wagons and, more people, but they didn't have electric machines yet. They didn't have air conditioning yet. They didn't have refrigerators yet. They didn't have antibiotics yet.
You say that. Is there no archaeological evidence that there was some sort of electrical, powered machine in archaeology going back?
Not like a light bulb or a motor or anything like that. No. Everything is radically changing right under these guys' feet. And they are, and a few women too, like Madame Curie and her daughter, but they are mostly men, and they're pioneering these unbelievable discoveries. And the Cavendish Laboratory is famous for doing everything on a shoestring. They're making all these discoveries with really simple ideas, really simple tools, and very little money. All right, so it was about 1911, depending on which paper we're talking about and what was published, but right about 1911, so right on the eve of World War I, is when they discovered what an atom was.
Okay.
We didn't know what an atom was before. We didn't have a definition of atom before this. We knew what an element was, but we didn't know what was inside the element. And what happened was you needed a whole bunch of things to come together at the same time. You needed a gold foil, no problem. You needed an alpha particle source, which of course is radon. And you needed an alpha particle detector, which today we call a Geiger counter. And so under Rutherford's direction, two men, one named Geiger, the other named Marsden, what they did was they took a radon source and they put it in a sealed container with a hole. And in front of that hole, they put a Geiger counter, or what would later on be called a Geiger counter. I don't know what the early versions of these were. Those are cool by itself because what it is you put an ionized gas inside a glass tube, and then you put a battery at each end and a speaker. And when a charged particle zips through that ionized gas, or maybe it zips through the gas that ionizes the gas, it lets electricity flow through the tube. And you get an ick. And every time you get another one, you get another ick, 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 ick. So you can literally count the pings with the Geiger counter. And so you put that in front of a radium, and it's going to go, it's going to be a whole bunch of pings. It's going to just sound like like white noise. But then you move it off to the side, and you'll hear nothing. And so you can move it in a circle around your radium source, and you can say, okay, there's no alpha particles anywhere around here except right in front of the Geiger counter, or right in front of the radium source. Radon. Oh, look at that. I'm confusing something here.
Oh?
He discovered radon gas, and I'm talking about radium. I wonder if they used radon in a sealed tube or radium, the solid material. I don't know. I got something else to learn. I jumped to radium.
Oh.
I bet they're using radium.
Okay.
And the things I was talking about earlier in the cloud chamber was radium, not radon. That makes no sense. Radon's a gas. You can't It'll float away. Okay.
Oh, okay.
But the radon's still true inside your basement. In the See, now I'm confusing myself. Hey, audience, I told Joe at the beginning of this that we're going to skirt the edge of what I know here. And I'm so worried about getting things right that I've already confused something that I already knew, and I got to confuse anyway because I'm so worried about what's coming. But this is part of the fun part of stretching one's brain and trying to wrap your mind around something that's really complicated. And all the other things we've talked about in the show, I'm pretty good at, but this is something that is right on the edge of what I know. So just admitting that for all of you, showing how much fun we're having.
Yeah, you're doing great.
So you take your Geiger counter and you move it around your experiment, and you can show that the only place you pick up alpha particles is directly in front of that hole. And now take a very thin gold foil and place it in front of your alpha particle source. If it's a plum pudding sort of model, those alpha particles are just going to go straight through that gold foil and hit the detector on the other side. In the same way, if you had a wall of sheetrock and you had a gun and you shot at that sheetrock, the bullet wouldn't move, would it? It would go right through the sheetrock, straight through. So if you had a target on the other side, boom, 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 your bullets go right through the sheetrock and hit the target. None of the bullets ricochet off and hit the wall on the left or hit you in the head or something like that. They don't ricochet. They go right through the sheetrock. The plum pudding model, it doesn't matter. Every alpha particle is going to hit the positive and negative charges. And so there should not be any angle to it. It should just go straight through. It might slow down. Maybe it would bounce off and come straight back at you, but they shouldn't scatter. But that's what happened. They picked up a lot of alpha particles that went right through the foil, but then as they took the detector and moved it left and right around in a circle around their apparatus, they realized that way off over here and way off over there at very weird angles, they were picking up scattered alpha particles. And the only answer to that was elements, or the atom, must be made of very discrete little compact particles, such that most of the time the alpha particle zips right through and doesn't touch anything. But every once in a while, it hits one of those little particles and bounces off. Hence, the Rutherford experiment taught us that there must be a nucleus.
So can you explain what a nucleus means? Because again, that sounds like, to me, it sounds like the skin on a grape. Like it doesn't sound like it would have to do with an atom. It sounds like skin.
Okay, just like in the cell, there's a nucleus in the cell. It's just a little round thing in the middle of the cell. Well, an atom has a nucleus also. So
it's not on the outside, it's on the inside.
Yes. And they did not know that until 1911. Cool. So now we know that atoms are made up of discrete little particles that are separated by themselves widely. And they figured out that all the positive charges, not necessarily this year, but they did figure out pretty soon that all the positive charges are concentrated in the nucleus, and all the negative charges, the electrons, are widely distributed through the substance. So it's actually the opposite of the plum pudding model. It wasn't like the electrons are little teeny particles in a positive charge. No, it's the positive charges are the little teeny particles inside an electric charge.
Okay.
And now we have atomic theory.
Wow.
For the first time ever.
Wow. It's hard to believe that all this is just so recent.
It's unbelievable that this is so recent. Rutherford in 1919 figured out that the proton was a hydrogen atom. And then a guy named Chadwick in 1932. Now, he had gone to Germany right before World War I and got thrown into a prisoner of war camp for the whole war. But while he was there, he did some experiments. He bummed some radioactive toothpaste from some German guards, because back then radiation was good for you.
But you mean that it was, or that they thought so?
No, they thought so.
Okay, because I was going to say, what was the expiration date on radiation being good for our grandparents?
So they literally had radioactive toothpaste, and it was a health thing. Yes. And so he got some, and so he was doing scientific experiments in the POW camp with metal foils and radioactive toothpaste. The guy's crazy. Anyway, he comes back in 1932. He figures out there's something called a neutron. And he won the Nobel Prize for that in 1935.
Wow.
Under Rutherford's direction, working in Rutherford's lab. Could you imagine making discovery and 3 years later you get $1 million check? I don't know what the prize was back then, but today's I think it's about $1 million. That's just amazing and cool.
It is. Unimaginable. You could buy a lot of radioactive toothpaste back then. Man.
Oh, yeah. Not a good idea. Anyway, we know what electrons are. We know what protons are now. We know what neutrons are. We know alpha decay and beta decay. We know half-life. This is really cool.
Yeah.
But what's inside those things? If you can smash a bar of gold, can you smash the atoms that the gold is made out of? And if we know that some atoms spontaneously decay, call that radiation, radioactively decay, into particles, those particles are coming out of the nucleus. Can we break a nucleus apart and see what's inside it? And the answer is yes. But to get there, we got to back up a step, go back to the 1800s, and we have to understand Coulomb's law, Gauss's law, and the Lorentz force. Now, no, we're not going to talk about those things. Let me introduce something called the right-hand rule, because this is going to explain everything that comes next.
The right-hand rule.
Make the thumbs up sign with your right hand, not your left hand, with your right hand.
Yeah.
Your thumb is sticking up and your fingers curl in a circle, right?
Naturally.
Okay, well, if you send electrons through a wire in the direction of your thumb, your fingers map out the magnetic field. It wraps around the wire in the direction of your fingers. So if you take a wire and you loop it into a coil, and then you send electricity through it, all the north poles and all the south poles are lined up, and you get an electromagnet. Now, a single wire with electricity running through it is an electromagnet. High tension wires have to be spaced far apart, or they can mutually attract each other and short each other out. Because a single wire is a magnet when there's electricity running through it. Now, this is discovered in the 1800s. I think, I forget the name. I'm going to kill myself later on, slap myself in the face for being so silly, but very famous scientist. He's got a compass on his lab desk. I think he was even giving a lecture, and he's connecting an electrical circuit, and he saw the compass move. And he disconnected it, and he connected again, and the compass moved again. And they discovered soon afterwards that moving electrical charges produce a magnetic field, according to the right-hand rule. This is incredibly important.
Okay.
This drives radio. It drives the old TVs, the old cathode ray tube TVs. It drives so much of our modern world. The idea that moving electrons, or positrons if you like, produce a magnetic field. And likewise, if you change the magnetic field, you can drive charged particles in a certain direction. Hence, the atom smasher is coming.
Okay.
But we have to get to the other Ernst. We have to get to Ernst Lawrence. But before we get to Ernst Lawrence, let me give you another version of the right-hand rule. Make the thumbs up sign and stick your pointer finger out like you're making a little gun symbol.
Yeah.
And now stick your middle finger out.
Okay. Now it's,
Again, right hand only. So you have 3 different fingers pointing in 3 different directions, right?
Right.
And they're all at right angles to each other.
Well, I got 2 down, 2 ahead, the thumb up. Yeah.
No, 1 forward, 1 up, and 1 to your left.
Okay. My left. There we go. Okay.
Right?
Got
it. Sorry. Since I can't see what you're doing. All right. Your pointer finger, if that's the direction of travel of an electron, your middle finger is pointing at the direction of the magnetic field, and your thumb is pointing at the direction of the force. Just trust me for a second.
Sure.
Since moving charged particles produce a magnetic field and there's a force involved, what happens if you shoot that charged particle near a magnet? It's going to curve.
Okay.
It's going to curve. That's how the old-fashioned television worked. You would literally, there's an electron beam aimed at your head, literally straight at you, and it passes by 2 magnets, one up and down magnet and one a left and right magnet. And by by oscillating those magnets back and forth really quickly, they can get the electron beam to scan across the surface of the television from the back side.
Wow.
And a phosphor lights up. That's how the old televisions worked.
Did not occur to me that it had anything to do with that.
It's all based on a moving electric charge produces a magnetic field.
Huh.
And because we know that magnets repel each other, right? Two norths repel, but a north and a south attracts. If there's a magnetic field around this charged particle, sending it near a magnet, it's either going to repel or attract. Cool, huh?
Yeah, it seems so primitive compared to television technology today, but
Yes, it does. Plasma TVs and all that. All right, so what happens if you have a large particle with the same charge as a small particle, and you send it the same speed past the same magnet?
Is that when you smash things?
Not yet. But obviously, the small particle is going to turn more than the big particle because the big particle has more mass and more inertia. It wants to go in a straight line.
Yeah, okay.
If you had a constant magnetic field, you could start figuring out how much charge is on a particle and the mass of the particle. Because big particles don't bend as much as small particles, and particles with more charge bend more than particles with less charge.
Okay.
Okay. And if you take a photographic plate and you sit it in your experimental chamber and you shoot two particles at each other, when they run into each other, they might blow up. And if they're in a magnetic field, the parts that result in this explosion are going to go left or right and make little curlicues and curves depending upon their mass and their charge. And after we started doing that for a while, we realized pretty quickly we always got the same particles.
Oh.
So it's not like, take a house made of Legos and smash it.
Yeah.
Every time you smash it, you're going to get a different collection of Legos, right?
Sure.
Depending on which one breaks where. But no, they always got the same exact curves, the same exact shapes, the same exact sizes and charges of particles. And they realized that at these energy levels, there's some pretty fundamental particles.
Seems pretty simple.
I'm trying to make it simple, and it really is if you think about it correctly. But the energy levels involved are unbelievable. I mean, even in a nuclear bomb, neutrons are not being exploded.
Really?
Yes.
Oh.
As neutrons are coming out of either plutonium or uranium, smashing into other atoms, making more neutrons spill out of those, you get a chain reaction. But the neutrons aren't being destroyed. So you're splitting an atom, but you're not splitting what the atom's made of. But you can split what that atom is made of and find out what it's made of. So neutrons and protons are made of other things. Okay. Ready for Ernst Lawrence?
Yeah. Okay, gonna roll up my sleeves.
The most famous person no one knows about.
The other Ernst.
Possibly the most important scientist ever that no one knows his name, except for one famous place, the Lawrence Livermore National Labs.
The importance of being Ernst.
It's funny. I don't know who Livermore was. So he's even less famous than Lawrence. But at least Lawrence has a national labs named after him. I read this book several years ago. In fact, I think I listened to it. Amazing book. It's called Big Science. Ernst Lawrence and the invention that launched the military-industrial complex. Do you know what he invented? The cyclotron.
Oh.
He figured out that if charged particles bend in the magnetic field, you can make them go in a circle. You can bend it a little with this magnet and send it through another magnet, which will bend it a little more, send it through another magnet that'll bend it a little more, and you can make it come back to where it started.
I'm looking at an example of a cyclotron right now.
Okay. Is it a small machine or a big machine?
It looks small.
Well, okay, the first ones were pretty tiny. Small energy, small velocity, but that first generation, maybe second or third generation of cyclotrons was used to separate the plutonium atoms.
Okay, in these examples, I'm seeing some old black and white photos.
Okay.
And this thing is big.
Okay, well, the first ones were literally the size of a desktop. And now we have ones that are underneath Switzerland and France.
No.
So they had to get bigger and bigger and bigger to do the next set of experiments. But what this guy did was he figured out that the shoestring budget of the Cavendish lab, yeah, they're going to do some cool things, but they got all the low-hanging fruit, and the next set of experiments was going to cost millions and millions of dollars, and every time you want to do the next experiment, the government had to pony up more millions of dollars. He started big science.
Huh. Wow.
And multiple people working on a project, not just one guy in a back room. A whole team of scientists spending many millions of dollars to do amazing things. So the first early cyclotrons, you could put plutonium inside the cyclotron and get to spin in a circle. But because it's going really fast, you could actually separate out the different plutonium isotopes. Because some plutonium atoms had a couple of more neutrons than others. They were heavier. They would require a stronger magnet to bend them. And so you could put all the plutonium in this thing, get it to spin in a circle, and the heavier ones would be flung to the outside. And he separated out atom by atom enough plutonium to blow up Nagasaki.
Oh, wow.
It was a couple of kilograms, maybe. But that's where that material came from, his laboratory in California. Now, why are atom smashers... Now, see, a cyclotron and atom smasher are similar. An atom smasher is you have these things going in a giant ring, and then you send something backwards. So they smash into each other, hopefully in front of your detectors. Or there are linear accelerators also, where they just in a straight line, it's sort of like a rail gun. They make the atoms go, or the molecule, or the particles, I should say, go faster and faster and faster and faster, and then they shoot it at something, like a gold foil or another beam coming at right angles or something like that. But why do these things have to be so big?
That seems really odd now that you say it, given the size of what they're trying to manipulate.
Yeah, talking about subatomic particles. Why do you need something the size of Switzerland to find out the next subatomic particle?
The only thing I could say is that anecdotally, computers started out huge, like hard drives and hard disks and
sure did
memory cards. Yeah, like
remember
computers
the 8-inch
were the
floppy
size of a floor. Yeah. Well, no, I don't, but I've heard stories.
I saw one once or twice.
So I'm guessing it's along the same lines for technology. They just were not, oh, man, I don't know how to explain it. Like, was it they just couldn't get it down to size?
No, it's the opposite. It had to get bigger.
Huh.
Okay, ready?
Yeah.
In order to bend a charged particle with a magnet, you need a big old magnet. If that particle is moving really fast, it has a lot of inertia. You need a big magnet to bend it, right?
Yeah.
The faster it's going, the more magnetic strength you need to make it curve. Does that make sense?
Yes.
Okay. Magnets have a limited strength. So if you want to make a really fast particle bend, you need a lot of magnets in a very big ring, and you better get the strongest magnets that you can make. So each one bends it a little teeny bit, and the next one bends it a little teeny bit, and the next one bends it a little teeny bit. You need a lot of magnets to make it go in a full circle. That's why they have to be so big. The second reason is that they will, as we're forcing these particles to turn in a circle, they bleed energy. So you can't make them in the tightest possible circle. They'll lose too much energy. It would take too much electricity to get these things to go at the speed you want. So we bend them a little bit so they bleed less electricity as they're making their little curving path. So we can keep enough energy in there that they're still going really fast when we want to smash it into something.
Yeah. Okay. Huh.
So they had to get bigger and bigger and bigger. And when we're talking about particles traveling at a significant fraction of the speed of light, I'm sure we'll have another episode on Einstein. In fact, probably more than one. But Einstein said, and according to all the experiments, it's true, the faster a particle goes, the more mass it has. And the reason we can't get particles hit light speed is because they have infinite mass. So even a subatomic particle, as it's running around these gigantic rings of magnets, that thing, it might not weigh almost anything, but at those speeds, it has a significant mass, and it's really hard to get that thing to change direction because of it. So we built the Large Hadron Super Collider, which is many miles in circumference, in order to be able to get little things to go really fast. And it's all coming from Ernst Lawrence, who pioneered a new way of doing science.
Wow.
And because of that, the United States took off even though the English and the French and the Germans, they did all the early work in figuring out what these things were, the United States said, thank you very much. And all of a sudden, we're building nuclear power plants and we're exploding cities with nuclear bombs and we're inventing things that no one else could do.
Right.
It was a technological and an industrial leap that was really pioneered by this one man. Unbelievably
Impressive.
cool.
Yeah.
All right. So how much time we got, by the way?
Well, that's about the running time of our usual episode right there.
I was kind of getting that feeling, but we haven't gotten to the standard model of elementary particles. So we're going to have to come back to it, I guess. How are we going to say, hey, that's it. I think all our brains are full. And we haven't talked about the electrons and the up quark and the bottom quark and how they combine to make things like neutrons and protons.
Which now I should go back and say at the beginning, digest this podcast slowly, maybe listen to it at half speed to absorb it all and make room enough in your head to get it.
Well, you can say that if you want to.
But yeah, so you want to continue talking about particles in next week's episode?
Well, you know, I did all the studying for this, knowing that we had to lay down a lot of background material in order to get to where I wanted to go.
Right.
And we just spent an hour talking about the background, which I kind of figured was going to happen, but I did hope to get to the standard model and talk about quarks and things like that. But yeah, maybe we can save it because that was a lot to digest right there.
Oh, it is, but it's good.
I hope so.
And it is.
Hey, listener, did you like that? Send us a thumbs up or a like or a comment. We would really appreciate it, by the way.
Yeah. And it is interesting stuff that you do make so much more digestible. There's only so much you can do to reduce science to its simplest form.
Thank you.
But you did a good job. So thank you everyone for joining us on this quest. If you want to dig deeper into these topics, you can find links to anything that Rob was discussing with us in the show notes of this podcast on our website. Hop over to nightowl.fm/equinox/20. Or if you're right there, the show notes are also with this episode in your podcast app. If you're listening to this on YouTube, you'll just need to go over to the podcasting app or to the website to get those links. You should also check out Rob's content on biblicalgenetics.com. That is the easiest way to find his other videos. His Facebook page or his YouTube channel are by the same name, where you can see the videos and join the discussions in the comments. And if you want to catch up with me, I am at JCS Darnell on Twitter. Until next time, goodbye, Rob.
Goodbye, Joe.
And thank you. You have been listening to Equinox.